Example 3, here are some sequences that don't have a simple defining equation. A, the sequence open bracket P sub n close bracket where P sub n is the population of the world as of January 1 in the year n. B, if we let A sub n be the digit in the nth decimal place of the number e, then open bracket A sub n close bracket is a well-defined sequence whose first few terms are open bracket 7, 1, 8, 2, 8, 1, 8, 2, 8, 4, 5, and so on, close bracket. C, the Fibonacci sequence, open bracket, F sub n, close bracket, is defined recursively by the conditions f sub 1 equals 1, f sub 2 equals 1, f sub n equals f sub n minus 1 plus f sub n minus 2. N greater than or equal to 3. Each term is the sum of the two preceding terms. The first few terms are open bracket 1, 1, 2, 3, 5, 8, 13, 21, close, and so on, close bracket. The sequence arose when the 13th century Italian mathematician known as Fibonacci solved a problem concerning the breeding of rabbits. See exercise 83. Text. A sequence such as the one example 1a, a sub n equals n over n plus 1, can be pictured either by plotting its items on the number line as in figure 1 or by plotting its graph as in figure 2. Note that since a sequence is a function whose domain is the set of positive integers, its graph consists of isolated points with coordinates. Um, Coordinate 1 and a sub 1, coordinate 2 and a sub 2, 3 and a sub 3, n and a sub n. From figure 1 or figure 2, it appears that the terms of the sequence a sub n equals n over n plus 1 are approaching 1 as n becomes large. In fact, the difference 1 minus n over n plus 1 equals 1 over n plus 1 can be made small as we like by taking n sufficiently large. We indicate this by writing the limit as n approaches infinity of n over n plus 1 equals 1. In general, the notation, the limit as a sub n equals the limit as the limit of a sub n as n approaches infinity equals big L, means that the terms of the sequence open bracket a sub n close bracket approach big L as n becomes large. Notice that the following definition of the limit of a sequence is very similar to the definition of a limit of a function at infinity given in section 2.6. 1. Definition. A sequence open bracket a sub n close bracket has the limit big L, and we write the limit of a sub n as n approaches infinity equals big L, or a sub n uh, goes to big L or approaches big L as n approaches infinity. If we can make the terms a sub n as close to big L as we like by taking n sufficiently large, if the limit as n approaches infinity of a sub n exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. Figure 3 illustrates definition 1 by showing the graphs of two sequences that have the limit big L. Figure 3 as the limit of a sub n as n approaches infinity of big L. A more precise version of definition 1 is as follows. Definition 2. A sequence a sub n has the limit big L, and we write the limit of a sub n as n approaches infinity equals L, or a sub n approaches big L as n approaches infinity, if for every epsilon greater than 0 there is a corresponding integer big N, such that if n is greater than big N, then the absolute value of a sub n minus big L is less than epsilon. Definition 2 is illustrated by figure 4, in which the terms a sub 1, a sub 2, a sub 3 are plotted on a number line. No matter how small an interval, open big L minus epsilon and big L plus epsilon close is chosen, there exists an big N such that all terms of the sequence from a sub big N plus 1 onward must lie on that interval.